So, we are back to kinetics. And here's basically the question that I set in last year's exam paper. For an experiment, you need to grow a culture of E. coli in liquid medium. At certain time points, small aliquots of the cultures are removed, and the absorbance is measured in a spectrophotometer. And this is what you get in terms of data. So you let the culture grow for the indicated time, here in minutes, and then you measure the absorbance. Okay? And what you see is, obviously, the longer you grow the culture, the more bacteria will be in there. And you can tell that because the absorbance is increasing in that direction. Okay? It's a fairly simple experiment that you do, but it's one of the very common experiments also when you work with bacteria. Now, one of the first question was basically, demonstrate graphically that the growth of this culture follows a first-order reaction. Okay? Now, how could we do that? How could we approach this question? Now, we know that, well, what we could do is we could plot these data here. And we would see something like that. So we plot the time here. And we have the absorbance here. And what we see is that originally we have a very low absorbance at time 0, but the longer we wait, it goes like that. Yeah? And if you do that, you will see that this happens. Now, this in a way, this doesn't look anything that we have dealt with before, does it? Because before, we looked at reactions where we, for example, had the consumption of a reactant. And when we plotted that, we plotted time and concentration of A, for example. And what we found was that we had something like that. You remember? Vaguely. So that was for the consumption. And that, we said, was a first-order reaction. Now we have the growth of something. What can we do? How did we say we could show that something like that here is actually a first-order reaction? Can you remember what we plotted? We said, okay, it's a first-order reaction, and what do we need to do in order to, get away from this curve? So we plotted time. And what did we plot here on the y-axis? What did we say we need to do? Loud. Which log? The natural log, exactly. It was the natural log, ln of A. And what did we get in this case? We got a straight line, exactly. We got something like that. Yeah? You remember vaguely? So that indicated the consumption, and because we got a straight line, This was indicative of a first order reaction. And we had to plot ln. That makes sense? Now, here we need to demonstrate that this one here, this curve here, is also a first order reaction. So what would be your suggestion? What could we do? Sorry? We do the ln of that. And the way we do that is we just simply plot ln absorbance versus time. And what would we get? Hopefully, a straight line. Which direction does the straight line go? Does it go down or does it go up? It goes up. Why? Because it's a growth. You are absolutely right. So the straight line would probably go like that. Yeah? And because it is a straight line, we can say that this must be a first order reaction. If we plot ln versus time. Does that make sense? So, this question asks us to demonstrate graphically that the growth of this culture follows a first order reaction. And all you need to do in this case is you plot ln of the absorbance on the y-axis. So you have to calculate, you have to calculate ln absorbance, so ln of 0.01 and so on and so forth, and plot that versus time. Your argument then is, aha, it's a straight line. If it is a straight line, then I know it is a first order reaction. Make sense? You have no other option than to say yes. So if you come across something like that, and that's a very common way of me phrasing it, demonstrate graphically that this follows a first order reaction. Actually, I noticed that in the exam, a lot of people said, oh, we didn't have enough time in this exam for this question. And I looked at their papers. And what they did was basically they started off with, ignore CNN, they started off with this one here, with a graph like that, where they plotted the absorbance versus time, and they got a curve like that. If I plot absorbance versus time, and I would get a straight line, what would that indicate? No, not necessarily. If I get something like that, there's still growth, isn't it? What would that indicate if it is a straight line, absorbance versus time? What? The order of the reaction is 0. So that would be a 0 order reaction. The red one, yeah? So in a way, people wasted time by trying to convince me that it's not a 0 order reaction. But you know that already, because it says here, it follows a first order reaction. So don't waste time trying to do things that you're not asked to do. And I think that would be always my advice when you do an exam. Rather than immediately starting writing everything that is in your head, analyze the question for a minute. This is time well spent. What does the question actually ask me to do? What do I know about the problem? In this case, I know it is a first-order reaction, so don't bother with any other thing. Yeah? That's a very important message. If you have been given a sort of the information that you have a dihybrid cross, and obviously not in my module, but in a different module, if you have a dihybrid cross, don't start with a monohybrid cross. It's just waste of time. You've got the information already. Okay? So, you've got 30% already by just simply drawing the right graph. And of course, what you need to do is you have to have the axes properly labeled with the right units. What would Ln absorbance have in terms of units? Yeah? You go like that? No units. Ln has never any units. Okay, so please no units. And is that label all right here on the x-axis, time? What's missing? It is, yeah, in this case it's minutes, but you're absolutely right. And then you would get 30%. Simple as that. Okay, so let me see. Okay, now for the next question. It says, calculate from the data provided the growth constant and the doubling time of the culture. OMG, how am I going to do that? Well, first of all, I know it's a first-order reaction. Yeah? So I can write down the equation for a first-order reaction, and I can write, for example, ln A final over A initial equals, and we said for the consumption of something, what sign would we have? Loud? We would have a negative sign for the consumption. You're absolutely right. But we don't have a consumption here. We have a growth. So what sign would you suggest? A positive sign, exactly. So we have a positive. And then we just simply have our remaining first-order equation, k times t final minus t initial. The difference between growth and consumption is just simply the sign here. So for growth gets bigger, it's positive. Consumption, this would be a negative, because it goes down. Okay? Make sense? God, I'm good. Now the next problem is, What are we actually looking for in the second question? What are we looking for? Calculate from the data provided the growth constant. What's the growth constant? K. Exactly. So we are looking for K. Right. Now, would be nice if we had anything given here, wouldn't it? Because we could rearrange this equation here and isolate K. So we could write ln A final over A initial divided by T final minus T initial equals K. That's what we're looking for. But, what do I have? What have I been given? Do I have anything of these things that I need? Okay, ln I can do. The fraction I can do. A final. Well, what we can do is we can just simply say we take 2 points on from our data. So we could say, for example, here, that's our starting condition here. That's the initial. And that's the final condition. So in a way, we can say, we can do a little table, if you like. And we can say, okay, A initial. This would be the absorbance, the initial absorbance, 0.01, and the corresponding time would be 0 minutes. Yeah? What would be A final? Very simple. It would be 0.1, you are absolutely right. 0.1. T final, in this case, would be, of course, 100 minutes. Yeah? And now I have all the information that I need. I need to write this nicer. I have all the information that I need to whack that in. So I can say ln A final, that is 0.1 divided by 0.01 divided by T final, that's 100 minus 0. This gives me K. I probably should say minutes here. Okay? Happy with that? With this transformation? Okay, ln 0.1. So what is 0.1 divided by 0.01? Loud? Yes, you are absolutely right. It's 10. Nobody said anything, but divided by 100 minus 0, I rather dare not asking you. I don't want to upset you. So what is ln 10? It's 2.30. And therefore, our K is 0.023. What's the unit? Per minute. minute to the power of -1, or 1 over minute. So that's our growth constant. Now it asks us about the doubling time as well. That's here. Now we need to find a way how we can convert this growth constant to a doubling time. Now we know that for consumption we defined what is called the half-life. Remember half-life? And we said the half-life is defined as ln2 divided by k. The beautiful thing is this equation here for the half-life also holds true for the doubling time. It's exactly the same thing. It's exactly the same. I just have the habit of writing it in a little bit of a different form so that I don't get confused. So I usually write it as 2 over 1. That indicates to me that it's doubling. Yeah? And it's ln2 over k. So I just calculated k. So my t doubling would be ln2. What's ln2? Loud? Somebody said? No, somebody didn't say? 1. ln2. That was a bit random. It's 1. Come on, try it out on your calculator. Divided by 0.023 minutes to the power of -1. What do you get when you do this calculation? Anyone? Roughly? 42. What? 34? You rounded a little bit much here, huh? Yeah, I thought so. Pretty much gives 30. What's the unit? Loud? Who's that? Minutes. You're absolutely right, because we have minutes to the power of -1 in the denominator, so therefore this -1 disappears and the minutes go up. And by the way, the unit for time is minutes anyway. It's not minutes to the power of -2 or something like that. It's minutes. So we have our doubling time. And we have our rate constant. Let's have a quick look at it. It means that every 30 minutes, our absorbance doubles. That is what doubling time means. And we can immediately check that. Let's have a look at, for example, 20 minutes here. We have an absorbance of 0.016. If we wait 30 minutes, we would be here at 50 minutes, and we would expect that our absorbance has doubled from 0.016 to 0.016. 0.032. And lo and behold, yes, it does. Hey, yeah, cool. We're good. So that is a little reality check that you can easily do, where you see, aha, my calculation is not that far off. If you had just, got a little bit wild with your decimals, and you would have found 3,000 minutes for the doubling time, you could easily see that it doesn't work, because then you would have to wait 3,000 minutes to go from, let's say, 20, from 0.016 to 0.032. It would take 3,000 minutes, and it's nonsense. Does that make sense to you? God, you are so quiet. Are you intimidated? Or are you just tired? Just want to go to sleep? Me too. If it's of any consolation. I'll tell you what, we do one more of these questions and then I let you go. Okay, it says here, the third question. Calculate from the data provided. You're not allowed to use the graph in this case, so you have to use these data. Calculate from the data provided at which time point the culture has an absorbance of 0.25. Can we already make a prediction? Loud? It must be between 20 and 50. You're absolutely right. So here is sort of the reality check. We predict from the data here that it must be between 20 and 50 minutes. Yeah? You are actually right. It's 0.25. Where is it? 0.25. You were telling me porkies. Sorry. 0.25. Okay, where's 0.25? After 100 minutes. Yeah. Sorry, I didn't pay attention. She was just smiling at me, and I just, I assumed that I missed it. Anyway, you came to my rescue, so it must be after or later than 100 minutes. Thank you very much for spotting that. It's not just you who is tired. Okay, so how can we deal with that? How can we calculate that? Well, actually, what we do is we do exactly the same thing that we've done before. We just simply say, okay, ln A final over A initial equals K times T initial, T final, rather, minus T initial. So what are we looking for? We are looking for time. After which time? So we are looking for this part here. And we can rearrange that. T final minus T initial equals ln A final over A initial divided by K. Wonderful. So what we need to do is we need to find our A final, our A initial. We've got K, we just calculated that, and we know that K is correct. So, let's start with A initial. We can choose this here as A initial. We can say A initial equals 0.01, T initial equals 0 minutes. Okay? A final in this case. Well, our final absorbance that we are looking for in this case would be 0.25. That is what we are looking for. What is T final? The corresponding number. Well, actually, that is what we are looking for. That's the time. Yeah? So all we need to do is now put these numbers that we have here into this equation. And we get T final minus 0 equals ln A final 0.25 divided by 0.01 divided by 0.023 minute to the minus 1. So far, so good? So all I need to do is calculate that. So I have ln 0.25 divided by 0.01 is anyone? Have I done it right? Hope so. Divided by 0.023 minute to the minus 1. And no, unfortunately, I can't do that in my head. So if you do that, you get 140. What? Bananas, apples, oranges? Loud? Minutes. It has to be minutes because it is the unit for the time. Now we've got a number that's great. And Donald Trump would say this is the best number in the world. And we really have great numbers, and I show you these great numbers because we do really great science. Okay, I don't want to get into politics here because that's that's a slippery slope. But it's a great number, 140, and it's a great unit, minutes. Now, does this number make sense? And again, we need to do this reality check. We said that it must be later than 100 minutes. Later than that one. We got 140 minutes, so that is a potentially good candidate. Are you happy with that? Fantastic. I'm not going into detail for the last question. Just show to you how you would do that. The last question says, calculate from the data provided the absorbance at 200 minutes. Do not use the graph. So how can you do that? What are we looking for in this case? We are looking for the number in this box. What do we know about this number? We know it's greater than 0.1. It must be greater than this one because we've got 200 here. Yeah? So it must be greater than the absorbance at 100 minutes because it's a growth. Again, what we can do is we can write ln A final over A initial equals K T final minus T initial. But now we have a bit of a problem. We say, for example, we are looking for this A final here. So our A final, that's what we're looking for. T final equals 200 minutes. A initial, we just take the first one, 0.01. T initial equals 0 minutes. So we are basically looking for this A final here. But we have a problem. It's in this ln. Bleh. Horrible ln. How do we get rid of an ln? We E it. E. I don't want anyone to go in the exam. E. Well, if you want to, feel free. What do we have on the left-hand side of the equation when we E it? What have we got there? E and ln cancel each other out, so we have A final over A initial. And what do we have on the right-hand side? Of course, we have E to the power of K times T final minus T initial. We can bring this A initial to the other side, and we have A final equals A initial times E K T final minus T initial. And now we can put things in. We said our A initial is 0.01. E times 0.023 times 200. And the rest is something for mathematical pedestrians. And you can just very easily calculate that yourself. Does that make sense? So in a way, there is a lot in this question in it. You have to draw a graph in this case. You have to interpret the data. You have to demonstrate that you can rearrange an equation. You have to demonstrate that you know how to use ln. And you have to remember a couple of equations. Challenging, but not impossible. Students who have chosen this question, on average, scored 78%. By the way, you get 3 questions, 3 problems, or 3 questions like that, and you choose one in the exam. Yeah? And you get also 30 multiple choice questions in the exam, and you do all of them. You've got 2 hours. Any questions for me? Everything absolutely clear as mud. Okay. Next week, we'll do a few revision things. Is that okay with you? Go in peace, have a good weekend, don't work too hard.